I am back once again to talk more about travel pads. So for those of you who might not have seen my other video, I've built a couple. This one on top is the first one that I put together. I was moving to a smaller space. I no longer had enough space for my arcade pad, and I needed something I could set up and tear down every single time I wanted to play. So I came up with this. It was really, really cheap, made out of OSB and poplar wood, just hobby wood. Used a center panel off my arcade pad, super duper simple, passed 17 on it, and nothing fancy. Just used knockoff FSRs, fixed resistors, a single Arduino Pro Micro. The biggest issue with it was that it worked a lot in the leaky shed that I play in. The wood wasn't treated in any way, so I had lots of issues with it, and honestly it just barely fit diagonally in a suitcase, a carry-on suitcase, so it wasn't even really suitable for traveling either. Later on, I came up with this pad on top here. This is a plastic travel pad made out of IKEA cutting boards, and the biggest, most attractive thing about it is that it actually fits in the bottom of a carry-on suitcase without any disassembly, doesn't need to be diagonal or anything. And it actually works decently well. It's a little bit wobbly, still uses the same knockoff FSRs, single fixed resistor Arduino Pro Micro that the other one does. Played some stuff on it. I don't use it routinely because I'm not having to travel with a single carry-on suitcase most of the time, but it is nice to have in case I need to do that. My main travel pad I've been playing on for quite some time now. I made a big video on it a while back talking about the whole design process, and it served me really well. Made out of metal, solid, doesn't move around when I play on it. It's actually held up surprisingly well in what's basically outdoor conditions, leaky shed that I play in. Really, there's been some corrosion on the hinges itself, but it stood up really, really well. However, I don't really want to talk about the hardware today. I want to talk about the electronics instead. So up until this point, I've been using a custom PCB that I designed specifically for this pad, and I designed this to be super duper thin so it fits in between the rails of the pad up here, and I don't have to worry about stepping on it or kicking it over or anything else like that. So really simple, 4 inputs for the FSRs, 3 outputs for the light strip that runs on all the panels here, and a DC 12 volt DC power jack for the light inputs. This runs great, but I've actually just come up with a new, you can kind of see it down here, a green PCB, new design, very similar form factor. It's a little bit longer, but sits in the exact same spot. And I will talk about why I did that and what are some of the pros and cons of each of these boards. I want to start by talking quickly about the old board that I designed originally for that metal travel pad. It's a fairly simple design, and it's based around the Arduino Pro Micro, which is socketed in place and has mounting holes underneath. It is a 4 FSR board. There are headers for the 4 FSRs, one for each panel down here. There's also a header for optional 12 volt LED lights. I use WS2812B light strips. And there's a barrel jack for 12 volt input power, reset switch, and a capacitor to smooth out any of that 12 volt change. Finally, there's also some SMD lights on the board itself, so these LEDs can light up when you're pressing a panel down, which means you don't need the 12 volts plugged in to tell you if a panel is being pressed. It can help you do diagnostics or bug fixing or pad modding as you go. However, the most interesting part about this board is this terminal block over on the side here with these orange kind of paddles on top. If you push these down, they basically will release the resistor, and this allows the resistors to be hot swapped. So say that you want a more sensitive or less sensitive FSR, and the range that you can adjust in the firmware is not sufficient, or maybe the deviancy in the range is not sufficient. You can actually just swap out the FSR entirely. So that was a really cool idea I came up with, but I only ever really used this feature once. I swapped these from like 1K resistors to 550 ohm resistors or something, and never really touched it again because there was no need to. So that was the original board that I had at first designed for the metal travel pad, and I actually have a bunch of them just like sitting here. I got these from a PCB manufacturer, and they had like a minimum number of boards, so I have a bunch that I never ended up using because I only have one pad that uses it. Next, I'd like to talk about the new board that I designed for the same travel pad. So it's a very similar form factor. It's slightly longer, but it uses the same Arduino Pro Micro, same mounting holes, and actually slots in the exact same spot. The barrel jack, capacitor, all that jazz are in the same spot as well, and the headers, for the FSRs and for the lights, are also in precisely the same spot, except a little bit further down, and that allows me to just basically one-for-one swap one board out for the other, depending on what I want. You'll notice that the resistor terminal block is gone here. It wasn't really a feature I used that often, so I replaced it with just simple vias, and I have the resistors just soldered in place here. These are certainly replaceable. You can just use a little solder wick or a solder sucker to remove them. I doubt I'll ever really need to, because I only ever swapped these once over the 2 years I've been playing on this pad. The big difference, I would say, is there's a second microcontroller on this board. This is an ESP8266 base chip called the ESP12E, and it's a tiny little Wi-Fi board that can run in access point mode. So essentially, this thing will look like an access point called, say, Travel Pad, and you can connect your phone to this chip's access point without needing any sort of Wi-Fi. So it'll make its own wireless network that you can connect to. And I set up a simple little logic shifter circuit that allows this 3.3 volt chip to communicate with the 5 volt Arduino and over I2C. And essentially what this does is you can change the thresholds. You can read the thresholds from the Arduino ZPROM. You can set and write new thresholds, which then get saved back to the Arduino ZPROM, or you can read the analog values coming back from the FSRs all through the web page that this tiny little chip is hosting. And what this essentially allows you to do is plug this whole board into a computer, and the only thing that the computer sees is the Arduino exposed as a keyboard or a joystick. I have this one configured to a joystick. You don't have to set up any of the Sujit software. You don't have to worry about serial ports or communication or any of that stuff. You can basically just plug it in, map the joysticks in Stepmania, and go. And any time you need to make a change, you just pull out your phone, connect it to the access point, and then change whatever you need to. There are big drawbacks to this. It's not a live preview. There's probably a way of doing that, but I don't know how, and I don't really know there's a need for me specifically to. So you have to pull it every single time you want to read the value on the chip, although you could use the lights to tell you if the threshold is being met. And you have to manually write the values as well. So every time you reboot this, it doesn't know what values are on the EEPROM, so you just read it back off the EEPROM, and then it'll show that in the web page, and I'll show an example of that later. And there's another built-in header as well. You can't just plug this chip straight in because it doesn't have a USB port. You have to use one of these simple little FTI adapters that you just plug into these lower header down here, but you can just program this using the Arduino IDE the same way you would the Pro Micro or a Teensy or anything like that. So fairly easy to use, all things considered. I think the last big feature about this is that it doesn't require any sort of external power input. This is low power enough that it can run off of a single 3.3 volt regulator, and the regulator's input comes from the raw power being supplied to this chip. So a single micro USB cable can plug into this guy up here, the same one that say would plug into this guy, and then there's the optional 12 volt DC power jack for the lights if you want, but it'll work perfectly fine without it. So this is more or less a drop-in replacement for anything that supported this old board, assuming you have the extra, say, 1/2 inch of extra board length that we didn't have previously. And like the other board, this one I also got from manufacturer, so I have a bunch of copies of these. I don't really need to make a bunch of copies unless I'm building more travel pads. Who knows? In the future, maybe I will. So here's a real quick demo of how the new board and software actually works. So like most other boards, you can press down the panels. If it exceeds the threshold, then the color is going to change. As you can see on this board in particular, those little SMD lights on the board are also lighting up and turning off as I press down and release from these panels. However, you want to adjust thresholds or read the values, then you'll need to go to your phone, connect to the access point that this microcontroller is exposing, and go to 192.168.1.1 homepage here. And what you'll want to do is read the sensors, and the color filled of these bars tells you just how hard the sensor is being pressed down on. So if I press down on the down arrow here with my elbow and then hit read sensors, you'll see that the bar exceeds the slider here, and that tells you that it's being activated. And of course the color is changed, and I don't know if you can see it, it changes on the board itself, which tells you that it's actually being pressed. Release it, that changes as well. The big caveat is that it's not live. You're going to have to press read sensor every single time you want to update it. So read sensor here, I think it's like right on the edge of being, oh yeah, it's super sensitive, right on the edge of being triggered here. So you can read the sensor, but say maybe you want the threshold to be higher. So you could drag this up higher here and then do write thresholds, or write, and now I have to press harder on it in order for it to activate. So it's no longer like hair sensitive like it was before. I kind of got to press on it. Again, it's not live. You have to manually read and write it. But the big deal is if you were to say reboot this, it doesn't know what the thresholds were at previously. If you just hit read thresholds, it will read the thresholds off the Arduino's EEPROM. So let's just screw up with the thresholds all over the place. Visually, blah, blah, blah. Okay, they're anything. I don't know what they are right now. Let's do read thresholds. It will adjust it back to whatever the EEPROM on the Arduino says it is. And then I can read the sensors again. And, hey, I'm beneath the threshold. And we can make it, say, more sensitive. And then write the threshold. And then when you read the threshold the next time, it'll just be whatever you had set it to. So pretty basic example. Definitely not as nice, not many as quality of life features as Sujit software, but it doesn't require anything to be set up on the computer beforehand. Hopefully that was a helpful little update on what the motivation behind this new board and why I would use it, when I would use it. I don't plan on using it routinely. I really like the features that Sujit software offers, and it's pretty kept up to date as well, something that I will definitely not do for this board. But if anyone wants to do something similar like this, I'll have the GitHub where I post all the information about this board and the CAD files, all that stuff in the description down below at some point, and hopefully you can make something that works for you.